final set of video chapters in this first module focusing in on the biological aspects of carbonate sediment, the diversity of carbonate grains, the various origin of carbonate grains and muds. I want to now pull all that material together and pull it into a classification of carbonates with a view to focusing on the textural complexity we see in carbonates compared to the much simpler assumptions that we can make in terms of classification for siliciclastics. Whatever classification we come up with in a carbonate, we have to make sure it encompasses the various biogenic origins, along with the degrees of diagenesis, both early and late, that we see in carbonate sediments. We need a different set of criteria. The image on the left is showing you quite clearly carbonates are biological, and they're either biocohesive, they're bound together, or they are loose mechanical accumulations of sediment, often derived from the breakdown of more biocohesive sediment styles. Any classification wants to define categories in which we can put something. George Henry Lewes, that prominent Victorian philosopher that lived in the second half of the 18th century, defines science as the systematic classification of experience. If we don't know how to classify something, we don't understand it. If we look at siliciclastic sedimentation, it's based on the assumption of weathering in the source area, transport into the depositional basin from outside. And so the two most important characteristics that we need to apply into classification of sandstones and mudstones is the nature of the physical energy in the depositional environment. And that has two main components, textural maturity and mineralogical maturity. This is Folk's 1966 classification. We could choose Pettyjohn's classification. Sandstone classifications tend to use grain mineralogy and maturity to read back into the likely provenance of sediment and also utilize the amount of mud we see preserved in that sediment as an indication of the levels of physical energy in the environment. We have a pure quartz arenite, what is typically considered a mineralogically mature and a texturally mature sample. Less mineralogically mature are the feldspathic arenites and the lithic arenites, with more labile components preserved in that sandstone. As we go back along the axis of mud content, percent of matrix or fine-grained mud, we're looking at levels of physical energy decreasing as we move from the arenites through the wackies into the mudstones. Quite a simple classification responding to the notion that siliciclastic sediments reflect physical energy in the environment and mineralogical or weathering maturity. What it doesn't consider, because it's typically secondary in any sandstone or wacky stone in the subsurface, is that diagenetic considerations are going to be secondary to compactional loss of porosity. Most studies of porosity and permeability in sandstones focus on the level of compaction in the sediment, with a primary focus on physical compaction, but also some chemical compaction with silica cementation later in the burial realm. For carbonates, things are much more complex than this simple response to physical energy, texture maturity, mineralogical maturity. Carbonate classification has to be more subtle than just the reflection of the energy levels in the depositional setting. We depend on the varying proportions of cohesiveness, biocohesiveness, or inorganic cementation. The proportions of sand, mud, and framework can be indicative of not just physical energy, but also has to include the concepts of syndeposition or mud capture, of allomicrite and automicrite, along with varying styles of biocohesion ranging all the way from coralgal frameworks into cryptalgal laminites or stromatolites or thrombolites. And we also have to include the notion of, if there is mud in the sediment, does that mud get winnowed out of part of the depositional setting? Then in carbonates, we also have that very important factor of post-depositional change or diagenesis, which is altering the style of rock that we see. This is a much more complex grouping of parameters that we have to try and capture when we look at classifying carbonate sediments. When we have any carbonate sediment, there are general depositional questions that we ask of that carbonate sediment. These questions are, what fossil groups are represented by the skeletal remains? Is there a high proportion of coral fragments or bryozoans? Are there particular species abundant, common, or rare? How are those skeletal elements and textural features preserved? Are they fragmented? Abraded? Do they show evidence of early or later dissolution? Have they been replaced? Has the depositional mud been recrystallized into microspar? How much marine cement is present versus later burial cement? What was the level of grain sorting and size distribution? So we look at the average and also the range of grain sizes, but also with the notion that micrite can be introduced in bafflestone environments, for example, in what are relatively high energy conditions on the seafloor. We also need to ask the questions of, have the bioclasts been bored? Were there micritic rinds from endolithic algae? Have the bioclasts been variably mineralized as we transform from aragonite to low magnesium calcite? Are there particular fossil group associations that tell us quite a bit about the depositional environment, phototrophic versus heterotrophic associations, deep water coccolith associations? These are all indicative of the depositional system in a way that we don't have equivalent concepts in sandstones. Carbonates primarily form within the basin of deposition and often are not transported too far from where they first form, whereas sandstones and mudstones, by definition, start to form outside the basin of deposition and then work their way into the depositional environment. The last thing we ask of the carbonate sediment is, depositionally, does the bioassemblage or its remains appear to be in situ? Was this a biocohesive sediment? Was it locked up as it was forming, or is there evidence of reworking? In any carbonate sediment, it's not just particle size, provenance, and physical energy we have to worry about. We have to think about it as something that's locally sourced. We have to think about it as grain size, because we grow the grains in the environment, is not necessarily a direct indicator of energy conditions. Even in clastic carbonates, the energy regime is demonstrated by the grain size of the matrix that hasn't been winnowed from the deposit. This is a different concept. We can have coarse grains, but winnowing of the finer grain material becomes the important concept. Not the size of the skeletal material, it's how much has been winnowed. We also have to ask ourselves, how much syndepositional cementation was there? Both biogenic cementation and inorganic cementation.